In this video, we are going to talk about the limit of a difference quotient. Now, this is one of the key concepts in calculus and one of the key limits for us, so we're going to spend a little bit of time here. Now, in order to understand the limit of the difference quotient, we need to talk about indeterminate forms. And so this is a special kind of limit where we can't at first glance tell what's going on. So first, we're looking at a limit of a quotient. So f of x over g of x. And we're interested in the limit as x goes to c of f of x over g of x. And if the limit as x goes to c of f of x is some number L, which is not 0, and the limit as x goes to c of g of x is 0, then this limit does not exist. Now, we will talk about infinite limits pretty soon, and so we're going to define what this is, but strictly speaking, this limit does not exist. Now, an indeterminate form is as follows. We're taking the limit of the ratio f of x over g of x, and the limit of the numerator is equal to 0, and the limit of the denominator is equal to 0. And it's called indeterminate because we can't tell, without a little more work, whether this limit exists or not. Now, very often, algebraic simplification is useful. Again, if f of x and g of x are both polynomials, then the limit x goes to c, f of x equals 0, means that c is a root of the polynomial, or the polynomial is divisible by x minus c. And if this were true for both of these, then we can do some simplification. Now, when we do that simplification, we may find that the limit exists, or we may find that the limit doesn't exist. We just have to do some more work to figure out what's going on. Let's do a few examples. So let's evaluate the limit as x goes to 3 of x plus 3 over x squared minus 9. So again, if we look at this and we look at the numerator, we have x plus 3. So the limit of the numerator, if we say f of x is equal to x plus 3, then the limit as x goes to 3 of f of x is 6. The limit, now if we let the denominator, we'll call that g of x, is equal to x squared minus 9. And we look at this limit as x goes to 3 of x squared minus 9, we notice that's equal to 0. And if we think about what's going on with this function, as x gets close to 3, the numerator is close to 6, and the denominator is close to 0, so it gets smaller and smaller and smaller. A number like 6, or any number, divided by a number which is getting smaller and smaller and smaller, is going to infinity, so this limit does not exist. Let's do another example. The limit as x goes to 2 of x squared minus 4 over x minus 2. So again, we look at the numerator, x squared minus 4, and we see what happens when x goes to 2. Well, that goes to 0. We look at the denominator as x goes to 2. And again, we notice that goes to 0. So here we have an indeterminate form. Now, especially with polynomials, the way to get around these problems is to simplify, to factor the numerator and potentially factor the denominator so that we can cancel some terms out. And then once we've canceled some terms out, we may or may not still have an indeterminate form, but we may be able to figure out a limit. And again, the reason we can do this factor is that when we're taking a limit, we never actually plug the number 2 into this, so we're never actually dividing by 0. So let's rewrite this. So this is equal to the limit as x goes to 2. And again, I can recognize the factors of the numerator. This is the difference of 2 squares. And so it's x minus 2 times x plus 2, all divided by x minus 2. And we notice we have x minus 2 both in the numerator and the denominator. Again, because we never plug in 2 exactly, we can divide those. And we end up with the limit as x goes to 2 of x plus 2, and now we can use our rules of limits to see that this is equal to 4. So again, we simplify, we see what happens. If we can simplify, then we might or might not be able to take our limit. One of the key limits in calculus is known as the difference quotient. So let's say we've got a function f defined in an open interval containing the number a. We look at the limit as h goes to 0 of f of a plus h minus f of a divided by h. Now we can immediately see this is an indeterminate form, right? So if we look at the numerator, as h gets small, this becomes like f of a minus f of a, so the numerator becomes close to 0. And again, as h goes to 0, the denominator goes to 0. So this is an indeterminate form, a limit of indeterminate form. Almost always, it's well defined. So interestingly, this is going to be one of those limits which we take and can do quite a lot with. Now, to solve this, we're going to use what's known as a four-step process. The first step is find f of a plus h. So remember, I'll just rewrite this here. So we've got it. The limit as h goes to 0 of f of a plus h minus f of a divided by h. So the first step is find this first term in the numerator. Second step, find the difference of the two terms in the numerator. The nice thing is pretty much always, sometimes there's a trick or two, but pretty much always that once we do this calculation in step 2, we find out every term has an h in it. Step 3, divide that by h, and step 4, take the limit. Now, because we were able to cancel out an h here, simplify this, we can often take this limit. So let's do some examples. Let f of x equals 3x minus 1 and find the limit of the difference quotient. The limit as h goes to 0 of f of 2 plus h minus f of 2 over h. Okay, so 1. We're just going to go through a process. And again, we will find eventually a much easier way to do this. But right now, we're just going to go through a process to practice our limits. So step 1, we want to find f of 2 plus h. Well, that's equal to 3 times 2 plus h minus 1. And let's just multiply all this out. We get 6 plus 3h minus 1, which is 3h plus 5. Okay, step 2 is f of 2 plus h minus f of 2. So that's going to be the result of step 1. 3h plus 5 minus f of 2, which is 3h plus 5. F of 2, if we plug 2 into our function, we get 6 minus 1 is 5, so minus 5. And as you see, that's equal to 3h. The 5's canceled. So the nice thing when we get to step 3, which is to calculate f of 2 plus h minus f of 2 all divided by h, we get 3h over h, which is just 3. And now we can take the limit. So for the limit as h goes to 0, f of 2 plus h minus f of 2 all divided by h is equal to the limit as h goes to 0 of 3, which of course is just 3. So in this particular example, this wasn't too bad. The 4 steps help us organize our work really, and especially when this gets a little more complicated, step 3 is sometimes a little bit hard to see, and so writing this out in this way helps us. Let's do another example. F of x equals 1 over x. So I suspect this is going to be a little bit less pleasant. So we want to find the limit of the difference quotient. The limit as h goes to 0, f of 3 plus h minus f of 3 over h. Now, we don't have to have a number 3. We could just leave this as an x, and sometimes we will. But let's do this with the 3. So f of 3 plus h, well, that's just 1 over 3 plus h. Step 2, f of 3 plus h minus f of 3. Well, that's 1 over 3 plus h minus 1 over 3. And now we're a little bit stuck here, except that when we have the difference of two fractions, what we normally do is find a common denominator and then take the difference. So we're going to do that. We're going to go ahead and do that. So this first fraction, we need a 3 in the denominator. So we're going to multiply by 3 over 3, and we get 3 over 3 times 3 plus h minus, now we need a 3 plus h in the denominator here, so we're going to multiply by 3 plus h over 3 plus h, and we get minus 3 plus h over 3 plus h times 3, being careful about those parentheses. And now we've got a common denominator, so we can combine these two. Then we get 3 minus 3 plus h in the numerator, which is just negative h over 3 times 3 plus h. Okay, step 3. Divide by h. And you can see the h has just come out here. So f of 3 plus h minus f of 3, all divided by h, equals negative h over 3 times 3 plus h divided by h, which is equal to negative 1 over 3 times 3 plus h. So kind of the amazing thing here is not only do we get an h coming out, but we actually end up with a limit we can actually take. So let's take our limit as h goes to 0. F of 3 plus h minus f of 3 all divided by h, which is the limit as h goes to 0 of negative 1 over 3 times 3 plus h, which again as h goes to 0, the numerator goes to negative 1, the denominator goes to 9, so that becomes negative 1 over 9. So again, a little bit more complicated, a little trick here in step 2, but it all worked out. Okay, let's do one more example where we've got a quadratic equation here. So we're going to compute the limit of the difference quotient, where f of x is x squared plus 4, and we're not going to bother with the a here, we're just going to find it for any x. So again, same process. Step 1, we want to find f of x plus h. This is going to be a little bit less pleasant. X plus h squared plus 4. I guess we should multiply that out. So we get x squared plus 2xh plus h squared plus 4. Step 2, f of x plus h minus f of x is what we just got, x squared plus 2xh plus h squared plus 4 minus, I'm just going to be careful with my parentheses, x squared plus 4, that's f of x. And if you notice, all of the terms without an h have just canceled out. And so we end up with, so the x squared cancel, the 4's cancel, we end up with 2xh plus h squared. Okay, step 3, f of x plus h minus f of x divided by h is 2xh plus h squared divided by h, which is 2x plus h. And now we can take the limit. I'm not going to write the difference quotient again. Be lazy. The limit as h goes to 0 of the difference quotient is the limit as h goes to 0 of 2x plus h. Well, the h goes to 0, and we're left with 2x. Now, if we had an a somewhere, we would have had an a everywhere, and this would have ended up being 2 times a. So that's our limit we've just gone through. Again, usual things, multiply things out. There's some more complicated ones which we haven't done yet, but there's some more complicated ones where you have to do a couple of tricks here and there. But basically, this almost always works.